Hey there, STEM students. This is Miss Ruark. We're in podcast 1.4, so we're going to talk about the history of the atomic model and one of the major models that came about. It's not the one that we go with anymore, but it's one that we need to use to understand a two-dimensional model of the atom. All right, so history of the atom. It all started back in ancient Greece with this guy, Democritus. He was a Greek philosopher, and he lived from 460 BC to about 370 BC. He was around during the time where Aristotle was around. He was a little bit older than Aristotle, and his mentor was Leucippus, who is the guy who originally came up with this theory that we call the atomic theory. Okay, now, Leucippus passed on, and Democritus, this guy, actually adopted this theory, and he went from this theory. He said that the universe is composed of two elements. One of them is the atoms, and the other one is the void in which these atoms exist and move. He called atoms atomos, which is Greek for atoms, and he's the first one to kind of come along and say that these atoms make up everything, and they are indivisible. They are everywhere. All right, well, we're going to fast forward a very long time because Aristotle came along and said, you know what, no, that's not true. There's those four elements, earth, wind, air, and fire, that make everything up. All right, well, a bunch of people in between here did a bunch of experiments. We'll talk about those in a later vodcast. And this guy right here, J.J. Thomson, he was an English physicist, and he was best known for his cathode ray tube experiments. Cathode ray tube experiments. Okay, so what he did was, this was a picture of a cathode ray, and inside of this is a sealed up glass, and it has a gas inside of it, and he would run an electric current from one end to the other, and what he noticed is that as he ran this electric current through this gas, that it started to light up and glow. See how it's kind of glowing here? Well, it started to light up and glow on the negative end, and it eventually would reach across towards the positive end. And he said, hey, that's pretty cool. So he tried it with another type of gas, and it still did the same thing. So he tried it with another one and another one and another one. And he said, you know what? Every single one of these gases are elements on the periodic table. They're all doing exactly the same thing, which is lighting up and glowing from this negative end towards the positive end. So he said, guess what? All atoms must have these negative charges in them called electrons. So he came up with his own theory of the atom, and he said that it was like plum pudding. So we call it the plum pudding model. And what that is that he said that there's these negative electrons, okay, the little blue things, those are negative electrons, and they're just kind of floating around. They're just kind of there, and they're dispersed in this red positive pudding. It's just positive stuff. I know a lot of people don't know what plum pudding is anymore. So I like to think of it as a chocolate chip cookie. If you look at this, it looks like a chocolate chip cookie would, right? Where the chocolate chips are just randomly dispersed through the cookie. Well, the cookie would be the positive matter, and the chocolate chips would be the negative. And that's what he said that the model of the atom looked like, because he was going on, hey, we don't know what's in this. Okay, well, behind him came this guy. His name was Ernest Rutherford, and he was from New Zealand. He was a New Zealand physicist, and he is credited with doing the gold foil experiments. Gold foil. Yes, they would take a piece of very expensive gold, probably wasn't that expensive at the time, and it was very thin. Because it's a metal, you can pound it really thin. It's malleable. And it was really thin, like a piece of aluminum foil. And so what he did was he set it up here with a piece of gold foil, and he had a source of alpha particles over here, which, if you don't know anything about alpha particles, they have a positive charge. And he would emit these alpha particles towards the gold foil. And he had a screen that went around it that would detect if the alpha particles would go through. Well, he said if J.J. Thomson's plum pudding model was correct, that most of this was going to be positive matter, and that the majority of these alpha particles should be coming back and he expected a good deal of them to come back this way and to just kind of be collected. Well, what he found out was that a good majority of them went through, and they were going through towards the back. They were being slightly deflected. Some of them were deflected to the side. You can't really see that color, I'm sorry. Let's do green. I like green. All right. Some of them were deflected to the side. Some of them came to this side. Some of them would come back to the ear. But the majority of them went straight through. And he said, hey, if these are going straight through, that means that there's only a small part inside of that element that has a positive charge. Because if there was a big part that has a positive charge, it would all come right back at us. But it's not. And so he said that there's a small dense nucleus. He said it's small and dense because it would have to be in order to let all those things go through, right? So small dense nucleus with positive charge is called protons. And this right here is what discredited the plum pudding model of the atom. Well, James Chadwick was an English physicist who was also working with Ernest Rutherford and J.J. Thomson. They all kind of worked together and worked with each other and knew of each other. And James Chadwick proved the existence of the neutron. Okay, and he won a Nobel Prize in 1935 in physics for his work with this. And just a little known fact about him, his nickname was... Let's see, where's my pen? Oh, I can't write it in green ink. That just wouldn't do it justice. His nickname was Jimmy Neutron. Oh, yeah. In case any of you don't know what Jimmy Neutron is, you need to go watch it. It's a cartoon. Brain blast. Awesome. Okay. Niels Bohr. Niels Bohr came up behind these guys after they have all discovered these different subatomic particles. And in 1922, he was awarded the Nobel Prize for his atomic model. And it's the Bohr atomic model. He did it based on hydrogen. And what he said in this atomic model is that the electrons are moving around the nucleus in certain energy levels. Okay. They go around the nucleus, they kind of orbit around the nucleus in energy levels, and he actually called them orbits. Like the planets go around the sun. The planets orbit the sun, right? The moon orbits the earth. Well, that's what he said that the electrons were doing. They were orbiting around the nucleus. And from this, we could also see, since this is a very dense, small thing, the mass of the atom is going to come from the nucleus. And the volume of the atom comes from the electron cloud, or the electron space outside of the nucleus. But don't say that it's electrons that take up all that space, because electrons are teeny tiny. It's the space that's there. It's a void that's there, and that's why there's so much volume to the atom. And then the electrons are just kind of located throughout. All right, so he had 4 principles with this. Oh, let me go back to that picture. Okay, real quick. The energy levels, when we have energy levels, we have, we designate them with a lowercase n. Now, you're going to see this lowercase n a lot, and it's going to be not just for energy levels, but for other things. Okay, so just bear with me. It is the symbol for a lot of stuff, but you'll know which one to use when, based on what our topic is. Okay, so energy levels. The one that's closest to the nucleus, of course, is energy level 1, n equals 1. The next one is n equals 2. Next is n equals 3. You keep going, n equals 4, n equals 5, n equals 6, 7, and you could probably keep going, right? Okay, and the electrons will fill into these energy levels in neat, nice, little ordered ways. Okay, we'll get into this very soon, but in the first energy level, so in n equals 1, it can hold 2 electrons. In n equals 2, it can hold 8 electrons. N equals 3, it can hold 18, and then we just keep going up and up and up and up. Okay, and like I said, we'll get into this more. It'll make sense, but I wanted to introduce that, so when we do get there, it makes a little, oh yeah, I remember her saying something about that. Okay. So, on to the principles. What did his principles say? His principles said that electrons only assume certain orbits around the nucleus that are stable Everything's looking for stability, and we call them stationary orbits because they follow that same orbit, that same path each time. He also said each orbit has an energy associated with it, and light is emitted when an electron jumps from a higher orbit to a lower orbit, and light is absorbed when it jumps from a lower to a higher. And remember, as you go out from the nucleus, the energy levels get higher and higher. Why? Because it's more energy to go from one to the next, right? So 1, 2, 3, 4, 5. Okay, and we keep going. And then the last one is the energy and frequency of light emitted or absorbed is given by the difference between the two orbit energies. So the amount of light, like on this hydrogen atom, remember we talked about how the lines or the light that's given off is broken into spectra, and we can see this would be an emission spectra because it's black here, and then it shows the different lines that are being given off. Now, if it was an absorption spectra, it would be continuous color, and then these lines right here would be black because the light would be absorbed. Anyway, so this yellow corresponds to a difference in energy levels between 2 and 3, and the red corresponds to a difference in energy levels. The green is a difference in energy levels, the blue, and so on and so forth. Okay? Well, there's only one problem with this model. There's always a limitation to all models, and the problem with this one is that it only worked for hydrogen. However, we still use it to show two-dimensional models of the atom because it is a nice way to look at the atom, because we know that atoms aren't two-dimensional, and we know that electrons don't follow the same path. They actually go around in orbitals, which is a three-dimensional region of space. And that leads us into the next vodcast, which will deal with the history of the atomic theory even more in depth, and we'll cover some more people. And yeah, this is good stuff. All right. And so here you go. I'll see you in class.